For the next 20 minutes, I want to shift gears and talk not about the electrons that are orbiting around the nucleus, but rather I want to talk about the nucleus itself and different phenomena that can take place within the nucleus. Specifically today, I want to talk about radioactivity. But before we do that, we have to show you a notation that we use as a tool through the rest of this unit. It's called isotope notation. If you take chemistry, or if you've taken chemistry class, you probably know what an isotope is. I define an isotope as a version of an element. An element has a certain number of protons and has a certain number of certain number of neutrons. If we have a particular element, let's say carbon, it will always have the same number of protons. Carbon at 6, uranium it's 92 protons. It always has the same number, but it doesn't always have the same number of neutrons. One isotope of carbon has 6 protons and 6 neutrons. Another isotope has 6 protons and 8 neutrons. So an isotope is same number of protons, different number of neutrons. Isotope notation will describe for us how many protons and neutrons a particular isotope of carbon or whatever else has. Here's what the notation looks like. X will always be the symbol for the element. So if we're talking about carbon, it will be C. Z stands for something that we call the atomic number. The atomic number is the number of protons. So for carbon, that would be 6. A stands for what we call the mass number. And the mass number is the number of protons plus the number of neutrons. For carbon, that could be 12. It could be 14. It depends upon the isotope of carbon or the version of carbon that we're talking about. We'll say in this case that we're going to have carbon 14. Another way to write carbon 14, by the way, we could write it like this, or we could just write it like this. All three of those notations mean the same thing. They're variants on isotope notation. Now, let's figure out how many protons and neutrons we have in carbon 14. Okay, if we see the first version of the isotope notation with 614, we'd know that carbon has 6 protons. The bottom number is always the number of protons. What if we're looking at the second one or the third one, though? How do we know how many protons carbon has if we're given the second one or the third one? Yep. No, actually you don't. So if we've got this given to us, this one right here given to us, carbon 14, or we've got this one given to us, carbon 14, we need to find the atomic number. Where do we find the atomic number? It's provided to us. Where? Yeah, it's on the periodic table. Okay, this is the first time you're going to use your periodic table in Physics 30. Okay, look on your periodic table right now, everybody. It's on your data sheet, the last page of your data booklet. You're going to find carbon, which is symbol C. It's over in the top right-hand corner. You see 2 numbers, 6 and 12.01. Ignore the 12.01. It's irrelevant to us. Always look at the smaller number. The smaller number is 6. That means carbon has an atomic number of 6. We don't need it to be given to us up here, although it's helpful because it helps us to skip looking at our periodic table. But if it's not given to us, just look at your periodic table and you'll see that carbon will have 6 protons. Always, always. Whichever version or isotope of carbon we have, it has 6 protons. Now, how many neutrons does this particular isotope have with a mass number of 14? Emma? Good. And we're going to get that by doing what? Good. 14 minus 6 equals 8 neutrons. How many electrons? That's an irrelevant discussion because we're not talking about the atom here. We're talking about the nucleus. And there are no electrons in the nucleus. We're talking about just protons and just neutrons. Isotope notation gives us all of that information, combined sometimes with our periodic table. Let's try one more example before we move on to where this actually gets used. Uranium-235. Oh, look at that. I didn't give you the number of protons. Where do you find it? What is the atomic number? Check your periodic table. Everybody find that now. That's a big mass number, right? So it's going to be like it's going to be way down the list on your periodic table. When we find that, if you need a little help finding it, you're going to find that at it's in the bottom, the very bottom row, towards the middle of the periodic table. What's the atomic number for uranium there, Kenley? 92. Okay, so that wasn't given to us, but we checked our periodic table. It was there. That means we have 92 protons. Regardless of the isotope of uranium, we have 92 protons. Now, each different isotope has a different number of neutrons. This particular isotope has how many neutrons? 235 minus 92 gives me 143 neutrons. Another isotope of uranium might have 92 protons. In fact, it has to have 92 protons and 146 neutrons. Same number of protons, different number of neutrons. You guys comfortable with that? All right. We're going to use that for the next several days as we talk about nuclear reactions, including radioactivity, that we're going to begin today, nuclear fission and fusion that we'll do early next week. Let's spend some time talking about what radioactivity is now. Radioactivity is a natural process. It is a random process. What do we mean by that? Well, it means that it happens on its own. We don't control it. We don't control whether it happens, and we don't control when it happens. It's like it's got a mind of its own. It's kind of like that spontaneous little kid, that spontaneous little 3-year-old that just says what he wants to say when he wants to say it. It's a process where a nucleus decays. It changes into something else. It's like alchemy. In chemistry, we learn that carbon is always carbon, and lithium is always lithium, and uranium is always uranium. But when we talk, but chemistry involves the atom with the electrons orbiting around it. As we look at nuclear physics, it actually is possible for one element to change into another element, but only by a nuclear reaction, for instance, radioactivity. Sometimes the nucleus is stable and it doesn't decay, but sometimes the nucleus is unstable and it does decay and change into something else. And we say that the resulting radiation that comes off of this, you end up, like let's say carbon-14 decays, it'll decay into nitrogen-14. So you're left with some other element. But there's also, in addition to that other element, ionizing radiation that's released as well. The ionizing radiation, or the radiation that's released, is ionizing, which means that it turns atoms into ions. Atoms that have equal number of protons and electrons, in other words, neutral things, it turns them into things that are charged. It turns atoms into charged atoms. Sometimes that doesn't make much of a difference. Sometimes it does. Okay, if we happen to consume something that's radioactive and it decays and produces ionizing radiation, then that ionizing radiation can turn atoms in our body into ions in our body. Why is that a big deal? Well, because those ions may cause chemical reactions to take place that aren't normally supposed to take place. And if you think about it, biology is just deep down chemistry. In order to have a biological function take place, it has to be a result of chemical reactions taking place. So if you've got chemical reactions taking place that aren't supposed to take place, then you get biological functions taking place in your body that aren't supposed to be taking place. You end up getting sick. Sometimes you end up getting acute radiation poisoning and dying fairly quickly as a result of that radiation poisoning. Organ failure, cataracts in your eyes, bleeding from your nose and your ears and everywhere else. Cancer, okay, is one of the common things that happen as a result of radiation poisoning long term. Okay, all kinds of biological things take place as a result of these chemical reactions that are taking place as a result of these bits of radiation byproducts that are ionizing atoms. So generally the rule of thumb is this: avoid nuclei, avoid nucleuses that are radioactive, that are not stable. All right, I'm going to list 4 types of ionizing radiation now. Remember, the nucleus in certain atoms is not stable, okay, for a number of reasons. And when that's not stable, it will decay into another nucleus and produce ionizing radiation. In the table that I handed out to you a few minutes ago, it lists 4 types of radiation that can be released. You also get the nucleus, right? The new nucleus, but these are the types of ionizing radiation that are released as the byproduct of the nucleus changing into something else. We first got alpha decay. Alpha decay occurs when you have really, really big nuclei. Not always, but often when you have really, really big nuclei. And as a result of that instability, we release some protons and neutrons. A chunk of the nucleus breaks off. That chunk of the nucleus has 2 protons and 2 neutrons. What else has 2 protons and 2 neutrons? Helium. In fact, an alpha particle is chemically indistinguishable from a helium nucleus. Now, I wouldn't suggest that you should fill your balloons with alpha particles and then consume them to try to talk with a high voice. Although the nuclei are exactly the same as helium nuclei. The difference between breathing in what's inside a balloon and breathing in alpha particles is that what's inside a balloon are helium atoms with the electrons orbiting around, instead of helium nuclei, which have a completely different effect on us. Alpha particles are matter. They have mass. In fact, alpha particles are helium nuclei. One alpha particle is exactly the same thing as a helium nucleus. The helium nucleus that you breathe in when you breathe in the helium inside a balloon, just without the electrons orbiting around it. Now, what causes this alpha decay to occur? What causes this, let's say uranium, this big uranium nucleus to decay into something else and give off this ionizing radiation that we call alpha, an alpha particle? Well, I said a minute ago that it occurs sometimes when you have really big nuclei. It occurs when you have really big nuclei because really big nuclei sometimes, relative to the number of neutrons, have too many protons. Nuclei are very finicky little things. If you have too many protons, the nucleus is unstable. Too many protons, that is, relative to the number of neutrons. Why? Well, there are 3 forces inside the nucleus, 2 of them that we care about for purposes of explaining alpha decay. There is the electrostatic force. Okay, the electrostatic force acts between protons and protons. The neutrons aren't affected by the electrostatic force. The electrostatic force is a repulsive force that acts between protons and protons. In other words, the more protons you have, the bigger the electrostatic repulsive force. But there's also another force that we call the strong nuclear force. That's an attractive force, and that acts between protons and neutrons. So if you have too many protons relative to the number of neutrons, then you get too big of a repulsive force relative to the attractive force. If the repulsive force is bigger, the nucleus splits up. If the attractive force is bigger, then the nucleus stays together. So what you want here is more neutrons, a higher neutron to proton ratio in order to make the attractive force bigger than the repulsive force. That make sense? If you have too many protons relative to the number of neutrons, then the repulsive force is bigger than the attractive force. And the nucleus will break apart. Remember that repulsive force is the electric force that acts between protons and protons, and the attractive force is that strong nuclear force that acts between protons and neutrons. So what happens here? Too many protons? Well, an alpha particle breaks off, which consists of 2 protons and 2 neutrons as well. But that improves the ratio of neutrons to protons, which means that the ratio of the attractive force to the repulsive force gets better. Now, that still doesn't mean it's going to be stable. The nucleus that results from this could still be radioactive in itself, but it's closer to being stable at least. Logan, you had a question? The weak nuclear force comes into play with beta decay. Although we're not going to talk about that, we're not going to deal with that, but that's where it does come into play. Yep.
So when you're saying
The question was when I'm saying when a nucleus or an atom changes from one thing to another, is it proton decay? Not exactly, I don't want to say proton decay, but the number of protons does change. So if I've got, say, uranium-235 with 92 protons, and an alpha particle breaks off of it, then now I've only got 90 protons. Does that make sense? Which gives me something else, like I believe it's thorium, actually. So in that case, we've lost protons. Now, when we talk about beta decay, it's going to look a little bit different, but even in beta decay, you're going to find that the number of protons is changing. It's just the mechanism is going to be quite a bit different. Yeah, can we? Fa, strong nuclear. I'll try to write that so you can see it a little bit better. The strong nuclear force is that attractive force that we want to win if we want the nucleus to remain stable. Okay, now let's talk about beta decay. There's 2 types of beta decay. One's beta positive, one's beta negative. We'll focus on beta negative first. Beta negative decay produces a particle that looks like this, which is exactly the same thing, not as a proton or a neutron, but it's exactly the same thing as an electron. So the nucleus releases an electron, which is odd because the nucleus doesn't have any electrons. How can the nucleus release an electron when it doesn't have any electrons to begin with? We'll see in a second here. A beta particle is matter. It has mass. It is an electron, which again is odd considering that the nucleus doesn't have any electrons, but see what I mean in a second here. Beta negative decay occurs because we have too many neutrons. Man, this nucleus is pretty finicky, eh? You get too many protons, then the electrostatic force of repulsion is too big. You get too many neutrons, the nucleus is energetically unstable. It's not a repulsive force that breaks it apart, but rather, here's what happens, and this is kind of odd. It's kind of like a club. We'll call it the nucleus club, all right? The nucleus club consists of what? You answer this question for me. The nucleus club consists of what? Who are members of the nucleus club? Yep. Good. Protons and neutrons in the nucleus club. Got it? The nucleus club gets together on Thursday night every week, and on one Thursday night they get together and say, guys, I think we got too many neutrons. What are we going to do? Somebody has a bright idea, kicking out some neutrons. And somebody else says, no, we like the neutrons. We don't want to kick out the neutrons. We like the neutrons, but we're just not stable. Something's just not working. So somebody else has another idea. Let's not kick out the neutrons. Let's just change one. Let's change a neutron into a proton. So now we have less neutrons, but we haven't kicked anybody out because we have another proton. We've changed a neutron into a proton. Does that kind of make a little bit of sense? And now the ratio of neutrons to protons is better, so it's a little bit more stable. But somebody else pipes up in the back and says, wait a second, we can't do that because that violates the law of conservation of charge. We had neutral, and now we have positive. Well, then the guy who had the bright idea of changing a neutron into a proton says, all right, then let's make an electron as well. Let's change a neutron into a proton and an electron. And then the guy in the back says, what's the guy in the back say? Electrons don't belong in the nucleus, club. Well, then the other guy says, well, then we'll kick out the electron. We don't care about him. Get out. We had a certain number of neutrons which made the nucleus unstable, energetically unstable. So we changed a neutron into a proton, which made it more energetically stable. But as a byproduct of that, an electron was also produced, which we kicked out. We kicked out of the nucleus club because it doesn't belong there. Remember we said a minute ago, it's kind of odd that you get an electron out of the nucleus when there are no electrons in the nucleus. Well, how do we get one out? We made one. We changed a neutron into a proton and an electron, and then because the electron doesn't belong, it had to leave. That electron that leaves is this. It's the beta particle. That's my beta decay right there. Now let's do one more with you here. See if we can finish this up here, okay? If the bell goes, just wait patiently just for a minute, okay? Beta positive is a type of decay that produces this particle. A beta, which is kind of like a handwritten B, Greek letter beta, +1. That's not a proton, by the way. That's a electron? What is that? That's a, go ahead. No, that's not matter either. That's antimatter. That's a positron. Just 1 second and we'll be done here, okay? This will go quicker. It's a positron. And that occurs, again, because you have too many protons. But it's not too many protons because the repulsive force is too big. It's too many protons giving us an energetically unstable nucleus. Man, is it ever finicky? Eh? You got too many protons, something can happen. Too many protons, something else can happen. Too many neutrons, something else can happen. That's why the vast majority of isotopes are radioactive. They're not stable because it has to be just right. That Goldilocks effect again. Right? It has to be just right in order to be stable. Here we have too many protons. It's energetically unstable. So what happens? The nucleus club gets together on Thursday night again and says, let's change a proton into a neutron. And, well, wait a second. The guy in the back pipes up and says, conservation of charge, remember, conservation of charge. What else is produced here? What else is produced? Question? Okay. What else is produced here? A positron. Positrons don't belong in the nucleus, so what happens? Gets kicked out. That's the beta plus particle, the positron that gets kicked out. Got it? Okay, we'll finish this up on Monday.